Welcome to this lesson on lift force, where we explore one of the most fascinating phenomena in physics, how airplanes fly. Lift is the upward force that allows aircraft to overcome gravity and soar through the sky. This concept is part of our fluid series, and today we will understand how the special shape of airplane wings creates this upward force using fundamental principles of fluid dynamics. By the end of this lesson, you will have a clear understanding of what makes flight possible. Lift force is the upward force that opposes the weight of an aircraft and keeps it airborne. For an airplane to fly, the lift force must equal or exceed the aircraft's weight. This force is generated by the special shape and movement of airplane wings through the air. At its core, lift is the result of air pressure differences that form around the wing's surface as the plane moves forward. Understanding lift begins with recognizing that it is fundamentally a consequence of how fluids, in this case air, interact with solid surfaces moving through them. The key to understanding lift lies in Bernoulli's principle, a fundamental concept in fluid dynamics discovered by Daniel Bernoulli. This principle states that as the speed of a fluid increases, the pressure within that fluid decreases. In simpler terms, fast-moving air creates low pressure, while slow-moving air creates high pressure. This inverse relationship between speed and pressure is crucial for flight. When air moves at different speeds over different parts of a wing, it creates pressure differences, and these pressure differences are what ultimately generate lift. The secret to creating different air speeds lies in the airfoil shape of an airplane wing. An airfoil has a curved top surface and a relatively flat bottom surface. When air flows over the wing, it splits into two paths. The curved top surface forces air to travel a longer distance compared to the flat bottom surface. Because the air molecules must rejoin at the trailing edge of the wing at roughly the same time, the air traveling over the longer curved path must move faster than the air traveling along the shorter flat path below. This difference in speed is what sets up the pressure difference we need for lift. Now let's connect the airfoil shape to Bernoulli's principle. The fast-moving air over the curved top surface creates a region of low pressure above the wing. Meanwhile, the slower-moving air along the flat bottom surface creates a region of higher pressure below the wing. This pressure difference between the top and bottom surfaces results in a net upward force. The higher pressure below literally pushes the wing upward toward the lower pressure region above. This pressure differential is the lift force that keeps the airplane in the air. Another critical factor in lift generation is the angle of attack. The angle of attack is defined as the angle between the wing's chord line, which is an imaginary straight line from the front to the back of the wing, and the direction of the oncoming airflow. At a small angle of attack, less lift is generated. As the angle increases to an optimal value, the wing generates maximum efficient lift. However, if the angle becomes too steep, the smooth airflow over the top surface breaks down and separates from the wing. This condition is called a stall, and it causes a dramatic loss of lift. Pilots must carefully control the angle of attack to maintain safe and efficient flight. While Bernoulli's principle explains the pressure differences, Newton's third law of motion also plays an important role in lift generation. Newton's third law states that every action has an equal and opposite reaction. As the wing moves through the air, it deflects air downward. The wing pushes air down, and according to Newton's third law, the air pushes the wing upward with an equal force. This downward deflection of air creates an upward reaction force on the aircraft. Both Bernoulli's pressure differences and Newton's action-reaction principle work together to create the total lift force. Let's summarize the key factors that determine how much lift a wing generates. First, wing shape. The curved airfoil design creates the velocity difference necessary for pressure differences. Second, air speed. Faster airflow increases the pressure differential between the top and bottom surfaces. Third, angle of attack. The optimal angle maximizes lift efficiency, while angles that are too steep cause stalling. Fourth, wing area. A larger surface area generates more total lift force. All these factors work together. Bernoulli's principle combined with Newton's laws of motion, along with proper wing design, make flight possible. Understanding these principles helps us appreciate the remarkable engineering that allows aircraft to defy gravity and soar through the skies.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.